This video assumes you've completed the CFW320 basic configuration video, this guy. You can control the spindle locally from the drive's keypad, and you have a switch configured to enable the CNC to control the drive. You'll also need an Altmill CNC machine with a working SLB-EXT controller, and you're now ready to configure it and the drive so the Altmill can control the CFW320 drive via PWM, which will then control the spindle. This is a list of everything we'll be doing in this video. We'll start by configuring the drive. And spoiler alert, there's nothing for us to do here because the CFW320 drive's default settings for remote mode are exactly what we need. We will quickly review each of these so you'll know how to make changes to your system if you need to. So really the only thing to do in this section is to wire everything up. Then we'll make sure gSender is set up correctly. And again, we'll be using the default settings, so that's already done. Then we'll test it, where we usually find out that the PWM converter is not set up correctly. So I'll show you a quick and easy way to fix that, and then we'll test it again and verify it. At the end of the video, I'll introduce how to make a drive ready indicator, how to automate dust collection, how to configure an unsupported custom drive for RS-45, and braking for fast deceleration times. And I'll share some resources you might find helpful. Now, if you're already familiar with how to do all this stuff and just need a list of what to do, take a screenshot of this slide and this schematic, stop the video, and go do it. For everyone else, stick around. I'll walk you through these steps and share some insights and tips so you get the most out of your Altmill CNC router with a WEG CFW320 Series drive. Here we go. The drive and CNC should both be on and ready to go. And don't forget to reset the e-stop on the Altmill. Go ahead and switch to CNC control and leave it there for the rest of the video. The Altmill's controller can send out a PWM signal to tell the drive what speed the spindle should be at. But the CFW320 drive doesn't have a PWM input. It does have a 0 to 10 volt analog input, so we need to add a little PWM to 10 volt converter board. I use this one from Amazon. You can use any one you want. They're all pretty much the same. Just make sure it has a potentiometer adjustment, takes a 5 volt 0 to 100% duty cycle PWM in, can handle PWM signals in the 1 to 3 kHz range, and can handle whatever supply voltage you have. I'll be using 24 volts, so this is great. Let's do the wiring first. This is the stuff we'll be doing in this video. Everything else was covered in the basic configuration video. On the Altmill's SLB-EXT controller, this connector is this guy in the upper left corner of the board. Wire the PWM and the ground to the PWM converter board. The board I'm using is labeled on the back. Then take the 0 to 10 volt DC output signal out of the converter board and connect it to the analog input 1 terminal on the drive and its common. That would be here on the drive's terminal strip. Finally, add your voltage source here. I'm using a 24 volt supply head laying around. Just make sure whatever you use can supply up to 100 milliamps of current. Okay, we just finished this part of the schematic. I do want to point out that this little PWM converter board connects all of these grounds, which means our analog and digital grounds are now coupled. I wish they had isolated the analog output, but we will be able to filter the analog input to the drive using parameter 235 if we need it. And I've never had to, so I think we're okay. On the CFW320 drive, there's a lot of space behind the cover for option modules, so I simply stuck the converter board in here with double-sided sticky Velcro. Let's set up the drive parameters next. Since we're using the default values for all of these, there's really nothing for us to do. So let's just take a quick look at them so you know what options you have available. There are lots of ways you can tell the drive what motor speed you want. You can use the drive's keypad or a remote keypad. You can use pulsed digital inputs or digital inputs as an electronic potentiometer, where one says accelerate, one says decelerate, and one is the run stop. You can use digital inputs to select preset speeds. Either analog input, we're using analog input 1 for this video, an analog potentiometer, RS-232, USB, RS-45, Ethernet, or even control it from the built-in PLC. It's crazy how flexible this drive is. Since we just told the drive to use an analog input to control the speed, Parameter 231 is used to tell the drive to use analog input 1 for that. The base drive only has one analog input, so of course it defaults to that, but if you plug in one of the optional I/O modules with an analog input 2 input, you would set parameter 236 instead. That's all you need to set up the analog input. Parameter 18 shows us what analog value is coming into the drive on a 0 to 100% scale. We'll use that a lot when we calibrate the PWM board in a couple minutes. There are some optional analog parameters that you can use to condition analog input. You can create a dead zone that sets the spindle speed to a min value up to a certain level. You won't have much use for that with a CNC. The gain is handy. For example, if you have a 0 to 5 volt signal coming in, you can simply double it here to get the full 10 volt range. Parameter 233 tells the drive what kind of input to expect. We're using 0 to 10 volt input, which can also be a 0 to 20 milliamp input. But you could use a 4 to 20 milliamp and even reverse the ranges of each of these. You can move the analog signal up or down 100%. And the main one to keep an eye on is this filter time. It defaults to 0, but if you get a lot of noise, you can use this to calm the analog signal down a bit. Now be careful though, if you use too large of a value, it'll slow the response time of the drive. I would recommend keeping it to a fraction of a second. Again, we didn't actually make any changes to the drive here. All of the defaults happen to be exactly what we needed. Okay, let's wire up the digital inputs. These guys. On the Altmill controller, in the upper left corner of the board, we just connect wires from these screw terminals along with the common. That connector looks like this. Those wires go to these terminals on the drive like this. Configuring the drive to use those digital inputs is also easy because, again, we'll be using all of the default values. Parameter 227 tells the drive how we want to control the run stop. We could control it from the keypad like we did in the previous video in local mode, via serial commands, Ethernet, or the built-in PLC. Again, we'll use the default of controlling it from a digital input. Parameter 226 tells the drive how we want to control the forward and reverse function. We could tell it to always go forward, always reverse, controlled by serial command, Ethernet commands, or even the built-in PLC. We're using a switch on the digital input, which is the default. Parameter 263 tells the drive what digital input 1 will be used for. There are tons of things that digital inputs can be used for, but we want it to be the run stop, which is the default for digital input 1. And parameter 264 tells the drive what we want to use digital input 2 for. We'll use it for forward and reverse control, which is the default for digital input 2. Parameter 12 shows us the current value of the digital inputs. The digital inputs appear like this in a single byte. I'm showing the inactive state first. So if we switch to remote control, yep, we get a 4. And then run in the forward direction, we get a 5. Hit reverse, we get a 7. Perfect. Being able to view and validate the digital inputs is a really handy feature of the CFW320 drives. So we really didn't do any drive configuration, did we? We just used all the default values and wired it up. Cool. Now let's go over to gSender and connect to the Altmill. I'm using gSender 1.5.7 for this video. Go to Config, Spindle Laser. I'll enable this guy and apply it so we can control the spindle from the main carving screen. These should all be in their default settings as shown here. If any of these are highlighted in yellow, like this guy, then they've been changed from default. The main thing is, make sure the generic SLB drive is selected. That automatically sends out PWM speed control pulses. Now this is important. If you change from something else like RS-45 control to this PWM control, then you'll need to hit apply and then power cycle the Altmill and do the e-stop thingy. If you're already in PWM mode, then you can usually skip the power cycle step if you want to. Well, we're done. Let's go back to the main carving screen, and down here we'll bring up the spindle control tab that we enabled a minute ago. If we try to run a spindle, nothing happens. If we increase the speed, there it is. If we go to the max speed setting and bring up a tachometer, we see we're basically at the spindle's max speed of 24,000 RPM. So that's good. But what's going on down here? We're telling it to go at 7,500 RPM, right? Well, here's the trick. These labels don't do anything in PWM mode. They're just labels. We need to adjust the PWM so it matches these labels to make these labels mean anything. So we'll need to specify a minimum PWM that gives us 7,500 RPM and a max PWM that gives us 24,000 RPM. Make sure the spindle speed slider is all the way down to the minimum position. Then go back to Config, Spindle Laser, and scroll down to PWM, and look, there they are, min and max PWM. Min PWM is the PWM signal issued when a slider on a previous page is all the way to the left, which is currently labeled 7,500 RPM. So we need to raise the min PWM until we actually get 7,500 RPM. I'm going to take a bunch of measurements and plot them so you can see what's going on. You don't need to do this. I'm just doing this so you can visualize what's happening. Then, once we see what's going on, I'll show you how to skip all this. So bear with me for a minute while I walk you through what I'm doing. I'll start the min PWM at 10% and then scroll up here to enable the spindle. Go to parameter 18, which tells us what the drive sees at analog input 1. I'll make a note of that analog value, stop the spindle, scroll back down to min PWM and bump it to 20%. Scroll back up and enable the spindle. Note what the display says the analog input is. Stop the spindle, scroll back down to PWM and set the min to 30%. Scroll back up, enable the spindle, and record that value. You get the idea. I repeated that in 10% increments all the way to 100%. Plot that, and we get this PWM versus analog voltage chart where the voltage is in percent of full scale. Well, that doesn't look any good. It saturates around 80% PWM. Clearly, the gain on that little PWM converter board needs to be adjusted down. To do that, just select a midpoint like 50% as the min PWM and adjust the potentiometer on the converter board until we see the analog input on the drive's display roughly at 50%. Let's do that. Set the min PWM to 50%, apply it, and enable the spindle. Adjust the potentiometer on a PWM converter board until the drive's display says the analog voltage is near 50%. I then went back and recollected the PWM samples over the entire range again. This time I got a curve like this. Much better. Nice and straight. But it still goes non-linear at the top end, and it never gets to 100%. This is pretty typical for these PWM converter boards. So to ensure a linear response over the entire spindle speed range, I've gotten in the habit of just using a 90% PWM as my top end. That avoids these kinds of issues, which means we need to raise the curve until 90% PWM gives us 100% analog input. To do that, I set the min PWM at 90%, hit apply, and enable the spindle. Adjust the potentiometer on a PWM converter board until I just get 10 volts out, or 100% on the drive's display. I then resampled the full PWM range again, and now our plot looks like this. Look how linear it is. A nice straight line and a 90% PWM now generates the max RPM, which for us is 24,000 RPM. So we enter that into the gSender configuration right here as the max PWM. Now we need to figure out which min PWM value will give us 7,500 RPM, which on our graph is 31.25% of 24,000 RPM. Now you could do this by trying different min PWM values until you hit 7,500 RPM, but it's a whole lot easier to calculate it using some high school algebra that says given 2 points on a line, you can always find a third. We'll use the 90% and 20% PWM values to calculate the one we want. These are the 2 points on the line that we'll use from that graph. We want to find the PWM for 31.25%, which is where 7,500 RPM is on a 24,000 RPM scale. Step 1, find the slope of the line. Put our values in, and we get this. Step 2, given the point-slope equation of a line, we put in our slope, one of the points, and a desired RPM in percent, and solve for the PWM value that will give us 7,500 RPM. Enter that here as the min PWM and accept it. Go back to the main screen with the slider all the way to the min PWM. Enable the spindle, and sure enough, we get basically 7,500 RPM. Go to the max value, and yep, 24,000 RPM. And you know it's linear from end to end. Perfect. Okay, remember, you don't need to go through any of this. I was just doing it so you could visualize what's going on. All you need to do is set the min PWM to 90% in gSender and adjust the potentiometer to get 10 volts out of the PWM converter board, which will show us 100% on the drive's display. Take one measurement at the low end and plug the results into the above equations. Here's the step-by-step procedure. Before starting, make sure the spindle slider is all the way to the left. First, adjust the top end. Go to Config, Spindle Laser. Scroll down to PWM, change the min PWM to 90%. Scroll up and enable the spindle. Adjust the converter potentiometer until the analog readout on the drive keypad just touches 100%. Now these potentiometers can be real touchy, so play with it until you get a solid reading. Usually going past what you want and coming back works real well. Stop the spindle. Second, measure a point near the bottom end. Scroll down and change the min PWM to something else. We use 20% in this video. Don't go all the way to 0. You can't guarantee it's going to be linear down there. Start the spindle. Note the analog value on the drive's display. Finally, do the math. Plug the 90 and 20% points into the math to calculate the PWM value we need to get 7,500 RPM, or whatever value you used on your minimum PWM label on the slider control. Put that result into the min PWM and put 90% into the max PWM, and finally go back to the main screen and try it. A couple notes about setting up PWM. This enables PWM output. I can't think of a time when you would ever want to change this, so just leave it alone. For example, if you decide to use RS-45 to control the drive, it automatically takes control. So even then you don't need to mess with this. You can tell gSender to stop the spindle anytime it gets an S0 command and to start it anytime it gets a non-S0 command. I haven't used that yet, but I suspect it might be useful when doing laser stuff. Earlier, we saw that the control signals out of the Altmill controller had the same polarity as what the CFW320 drive was expecting. If they didn't have the same polarity, we could invert them here. This is the frequency of the PWM signal. The converter we used can handle 1000 to 3000 Hz, so this is fine. If you get a board that needs something else, well, put that value here. Remember when we tried to run the spindle at the minimum value before we adjusted things and we got no spindle rotation? Well, that's because this guy forces the spindle to stop whenever you send it a 0 PWM or whatever value you put here. I can't think of a reason to change that, so just leave it alone. The minimum value label on the main page slider, this guy, is specified here. You can change it to whatever you want. Just don't forget to use your value in the math instead of the 7500 we used. Keep in mind, these inexpensive DIY spindles are not designed to operate at low speed. Usually they need to stay above 6,000 to 8,000 RPM. Below that, they'll draw a lot more current, get a lot hotter, and will definitely shorten their life and may even eventually burn up. 7,500 is a good, safe number to use. If you have a spindle that says it's designed for RPM lower than 7,500, well, yeah, go ahead and use it. Finally, you'll want to switch back to parameter 2 so you can modify and monitor the spindle speed. Well, that's it. We're done. Check out these videos to learn how to set up a drive indicator light so you know when the drive is on, and more importantly, when it's fully discharged and off. How to make your dust collector system automatically come on when the spindle's in use. We'll be using one of the drive's outputs to control that. How to set up an unsupported custom drive for RS-45, and how to add braking to get super fast deceleration times. And finally, Automation Direct has tons of videos showing you how to use WEG drives. Well, that's enough. Go have fun with your CNC.